All right. I guess we're ready to go. I would say welcome to this tutorial on Star AI and Neurosymbolic. This is joint work with Sebastian, Robin, and Giuseppe, whom of course you will all hear later today. It's also reusing some slides that are doing previous tutorials with people like Angelica, Christian, David, and Sriram. The latest version of the slides you can find on this address, and that should also have been entered in the chat, so you can also click there usually. Let me start by an introduction. And the motivation is something that you see a lot of times these days at AI conferences. It's like the quest for integrated learning and reasoning, the quest for AI systems that can do both thinking fast and thinking slow. And a lot of different terms are used for this. People use this System 1, System 2 of Daniel Kahneman. They use data-driven versus knowledge-driven, symbolic versus sub-symbolic, solvers and learners, and so on. And it seems that everybody in AI today agrees that this is like one of the big challenges of the field of AI today. And everybody agrees on that, even though the perspectives are different. And it includes both people, you know, from the classical knowledge-based approaches to AI, like Marcus, Darwish, Levesque, and so on. But also people in the neural network community, they firmly believe that this is like, well, the next frontier. What people don't agree about is how to realize this integrated learning and reasoning systems. See also the AI debates that have been ongoing. In any case, if you want to solve real AI problems, such as this one, which is something that self-driving cars would have to solve. And of course, it's also something that we have to solve, because if we pass, if we take the exam for our driver's license, we basically have to answer questions like this. And you'd also expect that self-driving cars are able to make the correct decisions in this. And of course, this requires both perception. You need to be able to identify where the entities, the cars, the pedestrians, the cyclists, and the traffic signs are. And then, of course, you also need to be able to apply the knowledge you have about traffic rules in general to be able to decide who can really go first. The main paradigm today for thinking fast is certainly neural networks. It's been amazingly successful at all kinds of perception tasks. The main paradigm for thinking slow is reasoning, or reasoning is logic and probability. And these are two main paradigms within AI that have been pursued for several decades. And what's interesting is also that their integration is well studied within the field of statistical relational learning, statistical relational AI, or probabilistic programming approaches. If you look at learning, there is the quest for integrated learning algorithms. It's a very nice read to read a book by Pedro Domingos on the master algorithm, and he describes 5 different paradigms, 5 different schools of thought that all have contributed their frameworks. And the question, according to him, is how to integrate these. Today, we're going to look at, well, 3 of these schools: logic, probability, and neural network. And that's what's going to come back into this tutorial, from Star AI to neurosymbolic. Of course, if you look at machine learning, there's a lot of combinations that study probability in combination with neural networks. I mean, after all, this is what deep learning is based on. If you look at logic and probability or reasoning, then that's what the field of Star AI is about. And also, Star AI has devoted a lot of attention and owes its success to a large degree to the fact that you can learn these probabilistic logics. And that's what we're going to build upon in this tutorial. There's also a lot of interest in combining the sub-symbolic and symbolic AI, like logic and neural networks. And that's a field known as neurosymbolic computation. That's also been around for quite a long time, but that is getting pretty popular today, thanks also to special sessions at conferences and special tracks also at this conference, if I'm not mistaken. And so the key message that we're going to have in this tutorial today is that these fields, one field, star AI, which combines logic and probability, and the other field, which combines logic and neural networks, or symbols and sub-symbols, that they share a lot of problems. And because they share a lot of problems, also many solutions apply to both of these techniques. And so we're going to start off by analyzing the state of the art in star AI, and we're going to map that to things in neurosymbolic. That is the path that we're going to set out today. And this may not cover all of neurosymbolic, but still it covers a fair bit of it. And there's also an accompanying survey paper that was published at the past HCAI. I'm now going to give the word to Giuseppe, who's going to talk a little bit about applications.
Yes, okay. Now just a brief list of some motivating applications which share this main idea that from logic and probability and reasoning from one side, and neural networks can both benefit from each other. From one side, we have the logic that can use, let's say, we have the neural network that can use the external knowledge provided by logic to improve its performances and use less data and generalize better. And from the other side, we can have neural networks that help logic-based system to reason more efficiently in general. So if you go to the next slide, we, as first motivating example, suppose that you have, let's say, MNIST digits, but you don't know how to map these images to the numbers, but you know the rule of addition. So the rule of addition provides you a kind of distant supervision, and you can use this knowledge to learn how to recognize the images, which is what is done in DeepProblog. And the next slide. For example, you can also use knowledge. For example, it's similar to the previous task, but here you have some kind of ontological knowledge. So you have some image recognition task. You have some parts that you have identified, and you want to detect which objects they are referred to. And you can use logic, of course, here. You can say, look, if something is a cat and you want to know what is a part of this cat, then maybe it's a tail or maybe it's a muzzle. And logic tensor network has shown that it can improve performances over classical neural network that segmentates and classify these images. The next slide. Okay, is also the case in which you want to reason over images. And of course, a neural network can do this, but has to learn to reason in many different domains, in many different situations, while a much better approach is what is done in neurosymbolic visual question answering, where which is this paper at NeurIPS 2019, where knowledge is used to provide pattern of reasoning, like counting or positioning in space. And this improves and simplifies the task for the neural network. The next slide is about similar, is still visual reasoning, but which is enhanced, for example, with ontological knowledge. This is a paper at IJCAI 2017. And here, the thing is that you can ask, for example, in this image, not only if there is a giraffe, but you can ask if it is an image related to zoology, for example. And of course, you have to add knowledge that is ontological here. And adding this is very simple in logic, but maybe not trivial just with neural networks. But finally, there is also the opposite path, for example, where you want to learn how to reason, for example, learn how to solve some task, a program for it, for example, inducting a program. But you want to use neural networks that learn from images and text to do this. And this is what is done in this paper, ACL 2018, where you learn from both images and text to learn program. And here, instead of exploring very huge space of programs, the neural networks helps you to learn the logical program in a much smarter way. So you see here this two nature of the application, where knowledge can help neural networks, and neural networks can speed up logical systems. So this is a common pattern in neurosymbolic application. So I leave the word to Luke again.
Okay, so I guess this was all illustrating the fact that you can combine knowledge and perception in this neurosymbolic knowledge being taken care of the symbol level, and yeah, the perception, of course, by the neural networks. As I said, the program that we set out in this tutorial is really to go from statistical relational AI to neurosymbolic and argue that they share a lot in common. And in order to provide evidence for that claim, we analyze the state of the art and we distinguish like 7 key dimensions. And what we're now going to do is go through all these 7 dimensions one by one. Some are more logic-based, others are more like probabilistic graphical model-based. And we're going to show how they come back in neurosymbolic computation, how you can exploit the results from this logic, from this probability in neurosymbolic, and vice versa, of course, why these results from neurosymbolic are also important for statistical relational AI. And that's going to be the core of the talk. Afterwards, there's just going to be some conclusions. And the goal is that we're going to stop after dimension 3 or 4 for a short break of about 15 minutes. And we're gonna start now with the first dimension, where which is kind of the logic dimension, if you want. In logic, there is like 2 different settings or interpretations. You can analyze everything from a proof theoretic or a model theoretic perspective. And what we're going to do is we're going to start with just looking at the logic. We're then going to transpose it or transform it to the probabilistic logics. And then we're going to show how this comes back in neurosymbolic. But let me start with just the logic. And in logic, this is like a standard kind of dimension. If you have a logical theory, you can look at it in 2 different ways. One is you can use it to prove certain things, and the other, you try to find models that satisfy the theory. And so that's like this 1 key dimension. And along the way, I'm also going to mention some other things about that are important for the rest of the exposition. And let me illustrate it with a gentle example, which is in propositional logic. It's also in the programming language Prolog, and it's inspired by the examples of Judea Paul on Bayesian networks. And you'll see we're going to transform it into Bayesian networks later on. So what you have here is in the box, in the orange box, there is facts, the fact that burglary is true, the fact that here's alarm Mary is true, the fact that there is an earthquake, and so on. And those are all facts. These are true things. And then you have also the rules, which are written in this funny notation where this means actually Mary calls if there is an alarm, and then comma stands for and. So if there is an alarm and Mary hears the alarm, basically. And so the rules together with the facts allow you to draw inferences. For instance, you can now prove that from this logic program that Mary calls is going to be a consequence. And here you see like 2 proofs for that. On the one hand, you see the proof that's going left. And what you've done there is, I'm not sure whether I can use the mouse here. That doesn't seem to work. So you see that if you look at the rules, then there is a rule where the conclusion part mentions calls Mary, and the condition part says alarms, here's alarm Mary. And so that's exactly what you derived in the first step, in a sense, from calls Mary to alarm, here's alarm Mary. That's the first kind of proving step. And then there is, you try to prove, continue, you try to prove alarm. And okay, for alarm, there's another rule. There's 2 rules, one with earthquake and one with burglary. And so there's like 2 options. And if you continue in that way, at some point you arrive at the empty things that are that you still need to prove And that's like when the proof is complete. And if one of these proofs is found, you can of course conclude that Mary indeed calls, that this follows from the program. The other perspective is more a perspective of using the logical statements as a kind of constraints, very much in the same spirit as you do in SAT solvers. Here you have like logical statements, they're rules, they're clauses, they are in a conjunctive normal form if you want. And so what a SAT solver would do, it would find an assignment of values to the variables in the domain. And the variables here are like cold, Mary, alarm, earthquake, and so on. So the goal would be to find a set of variables that if you make these variables true, then everything, all the rules are satisfied. And this is the possible wall that's indicated on the right. And the convention is that you only write down what is true. Everything that is not in this set, in this possible world, is assumed to be false. And that's the model theoretic perspective. Given this logical theory, this is a possible world, and there's possibly other possible worlds that will also satisfy this theory. And that's the model theoretic perspective. Another thing that's kind of quite important is the use of variables and grounding and domains. And here you see very much the same program, except that we've now distinguished these constants, Mary and John, and that in the bottom rule, we also have this variable x. And x can, of course, be substituted by all these elements in the domain. In this case, the two persons, Mary and John. And the meaning of such a program with variables is that you can actually ground out that program. And if you ground out that program, you get the program that's on the right. That's the grounded theory. And the meaning of the left program, the kind of relational or first order program, is really the grounded one that you have on the right. And there's more clever ways of grounding out things that you may want to use so that you only ground out what is really relevant. To do this model theoretic reasoning, there's various approaches. You can do the kind of forward chaining as is sometimes done in databases or in Prolog, or you can use the SAT solvers as I've indicated. And here are some examples as to how that would typically be done. And of course, also in the case of using these variables in this kind of Prolog programs, you can also do the kind of proving. And Prolog is, in a sense, a theorem prover for a certain class of logic programs. And what you see is that it automatically then takes care of these variables. You see that here the rules, which are on the top right, for smokes, they mention this variable. X is smokes when X is stressed, and then, okay, the proving will automatically take care of the right variable bindings, the right kind of substitutions that are important to kind of prove all of this. And so this is the first dimension. It's proof versus model-based, and that's just looking at logic. But as I argued, it's not just logic. From logic, we're going to go to probabilistic logics, and we're going to add directly the probabilistic graphical model dimension, because it turns out that what is proof-based in logic closely corresponds to the directed graphical models, and the model-based, the SAT perspective, closely corresponds to the undirected graphical models in PGMs and in StarAI. So let's look at this. I mean, there is like two prime representatives of StarAI models. On the right, you see Markov logic, which is, well, the semantics is given by undirected Markov networks. You see kind of rules, and the rules act as constraints, very much in a kind of soft constraint satisfaction, a soft satisfiability way. On the left, you see an annotated probabilistic logic, which represents a probabilistic graphical model, a Bayesian network that is directed. And so these are like two key representatives. So let me now argue or show how you go from this logic to the probabilistic logic using these two in these two cases. So this is what we've just shown, the proof theoretic perspective. And the key insight to get at the probabilistic logics, the key insight, which is due to Daisuke Sato and David Poole, is that in order to unify logic and probability, they actually go back to the simplest possible concepts in both logic and probability, the basic concepts, so to say. And for probability theory, these are like random variables. For logic, this is a propositional variable, and that by mixing these two concepts and saying that propositional variables become random variables, you in a sense unify, you build an interface between the logic and the probability. And it is this what is exploited in these probabilistic logic programs, this directed star AI systems. And so what is happening is that here, what you change is you keep the facts as they were, except that rather than making them true by mentioning them, you now make them true with a particular probability. In this case, burglary is supposed to be true with probability 10%, and Mary hears the alarm with probability 30%. And all the rest is actually remaining the same. You can then still do proofs for this. And here is a proof for alarm. There's two possible proofs for alarm, one building on top of the first rule and the other on the other rule. Alarm will be true if burglary or earthquake is true. And it's easy to compute the probability of a proof. It's just the product of all these facts that you encounter, all the product of the probabilities of these facts. But of course, you have to take into account this probabilistic, these probabilistic things, which basically say that if you want to compute the probability of alarm, well, there's two proofs, one relying on burglary and the other on earthquake. So the probability of alarm is the probability of burglary or earthquake. And given that you have an or, of course, you can't just sum up the probability of the two proofs. You also have to subtract the intersection of that. And because the two proofs could be true at the same time, there could be a burglary and an earthquake at the same time, and that probability has to be subtracted. And that is leading to some complications. You can also look at the setting in a kind of generative manner. What does it mean, such a probabilistic logic program? Well, that's indicated here. Again, you have a program, and then you have this tree, and the top of the tree is like this one node on top of earthquake, and that's representing the empty possible worlds. And then you're gonna look for rules that fire, and earthquake doesn't have any condition, and so earthquake is true. Earthquake should be added to the possible world, and that's the node that you find just below earthquake. That is going to contain earthquake and nothing else. And then if earthquake is in your possible world, well, you know that with probability 60%, alarm is also going to be in that possible world. And so you go left, and there you see like this possible world, now consisting of alarm and earthquake. On the right, well, you just copy the earthquake, and you can continue this process. You get a kind of generative process that allows you to enumerate all the possible worlds. And then in order to compute the probability of something like alarm, what you do, well, you just sum up the probabilities of the orange nodes, and the orange nodes are those possible worlds that contain alarm in there. The probability of these orange nodes is just the product of the probabilities along the path to that particular node. So the leftmost one is 0.6 times times 0.05 times 0.8. And that's also like, yeah, the first term that you find in this summation. And that gives you a bit the semantics of this. Now it's clear that with these programs, you can quite elegantly and naturally represent Bayesian networks. I already indicated that there's a one-to-one mapping from yeah, a CPT and the Bayesian network to such a program that I'll explain in just a minute. But let me also show that you can do much richer things. I mean, these probabilistic programs, they are a programming language, so you have much more expressive power. It's actually Turing equivalent. And so one of the things that you can easily do is represent things like this plate notation that you have here. Remember that in plate notation, what you have is a graphical model, and then there is these rectangles drawing around parts of this Bayesian network. And that plate, that rectangle, has to be repeated for certain of the variables. So here, there's a plate for S for students, there's a plate for C for course. And that means that this has to be repeated for every student and for every course. And that's very similar in spirit to what you get when you do ground out these logical series. So there's an analogy here between these variables like S and C and the grounding out that you get, the unrolling, as it's sometimes called in this PGMs. So here you see what happens if you have about 5 courses and about 5 students, and the thing is enrolled. The interesting part is that it allows you to make abstraction of the number of students. You can write down the models very compactly. And you can also learn over different instances. Maybe you learn from a school with 10 students, maybe you learn from a school with 100 students, and you can, in a sense, mix all of that. Furthermore, you can reason at the kind of abstract, at the kind of lifted level, as it is sometimes called and sometimes done. And it allows you to reason very flexibly. This is what you can straightforwardly do in this probabilistic programming languages. Here, what you would do is for every node in the graph, for every entry in the CPT, you would basically have one of the rules. And so the first rule here says that for every student, there will be this variable, the intelligence of the student, and with probability 40%, the student will be intelligent. For every course, the course will be difficult with probability 50%. You list all the students, you list all the courses, and then also for grade, there is different options. There's typically like 4 possible combinations now, 2 for the intelligence, 2 for the difficulty. And so you can kind of write that down. Every of these will correspond to one of the rules that you have here. So the first one says, if the student is intelligent and the course is not difficult, he will get an A on that course. And then the others are kind of similar. What's interesting in these logics is that it's very easy and straightforward to encode also ontological knowledge, like when are students doing excellent, when are the results unsatisfactory, and so on, basically. This kind of probabilistic logics has been used, it has been developed over many different years. I mean, Sato and Poole go back to the 90s, the early 90s, and there's been a lot of applications. One application is where you have like online games and you want to model how the state evolves and what's going to happen in that state. You can do it to reason about objects and about occlusions in robotics. You can use it to recognize activities. There's other applications where people have used it to kind of learn the effects of actions in a kind of continuous strips-like representations. And then this is used to do a kind of planning. So there's a series of papers on that, also in biological domains. this problog and variations and this probabilistic logics have been used to kind of uncover and explain the causes for certain activities and certain interactions in these biological networks. So there's a lot of stuff around that. If you're interested in playing with this, I'd suggest you look at the Problog language and you try it out on the web. The other framework in Starry, so this was the directed version, the proof-based version in the first dimension, but there's also the other version, which is undirected as a graphical model, and which is more in the spirit of this satisfiability. It's called Markov logic. And what you do there is that rather than require that possible walls must satisfy all the constraints, the degree to which they satisfy will have an effect on the probability with which these possible walls are true. And here is an example. If you have a logical formula like that, and you then have like friends and happy, then there is this statement, the formula says, okay, either Bob is happy or Anna is not a friend of Bob. Well, the kind of possible worlds where this will be true are indicated here in the sense. There's only one possible world, namely the world where happy Bob is false and Anna is a friend of Bob, where this is not satisfied. And now what's going on in Markov logic is that, so here you get a kind of 1-0 possibility, either the yellow, you're in the yellow part, and then you get a possible world, you're in the white part and you get an impossible world. And what Markov logic is doing in an elegant way is really making, if the world does not satisfy a constraint, it doesn't become impossible, but it just becomes less likely. And that is what Markov logic is about. You can then use this to set like weights for the formula. And it is also viewed as a kind of can be viewed as a graphical model. Here you see some of these logical constraints. Smoking causes cancer. It happens in many situations, but not in all. So you can't say it's a certainty. And you see also the weight 1.5. And the idea is that it encodes also, you can view it as a probabilistic graphical model, as is indicated here. You have two people, the domain is Anna and Bob. And so these are the possible variables that you get for the first rule. There's smoking, there's cancer. If you look at the second rule, then that's about friends, and either the two friends will both smoke or yeah, they will not smoke. And that's what the second rule is saying. And so here are the other things. And what is then done is that Markov logic, in a sense, yeah, the semantics of it is given by an underlying probabilistic graphical model for which you can derive a kind of probability for worlds that satisfy it or not. I'm not going to go into detail about the formula. Giuseppe is going to talk about that a bit later in a bit more detail. Also for Markov logic, there's zillions of applications. I suggest you go to the website and you look at several of the applications. And so if you look at the PGM and the star AI dimension, then what you see is that again, you have like these two representatives. There is the directed, which correspond to more the proof theoretic version. You have the undirected, which is more like the constraint-based, the satisfiability based, or the undirected based, or the model theoretic based. And these are like two key representatives. What's also the case is that there is this, that the same kind of division carries over to neurosymbolic, because also there is like this dichotomy between these two types of systems, one which you could call a kind of neural program, and the other is more where logic is used as a kind of regularizer, as a kind of constraints on the neural network, and that is what is used. At the same time, you've seen that while I was explaining the starry eye systems, what you also had is that, for instance, with this Markov logic, you would generate a probabilistic graphical model. The logic would be used as a template to generate that undirected Markov network. And that is what is sometimes called knowledge-based model construction. And also that element that is so prominent in starry eye, and that's in a sense also the grounding out to some extent in the logic, that also comes back in neuro-symbolic. And let me just illustrate this on a couple of examples. So here you have one of the earliest approaches that is due to Shavlik and Towel. It's going back to the 90s. It's in a system called K-band, and I see that the reference has disappeared from the slide. But what they do is they work with this propositional series, very much like the series that we've seen for the alarm and the calls Mary example. And then the goal is that starting from these basic features like ST, G, and so on, they want to predict whether A is going to be true or not. And so what they do is they go through, they start from this logical theory, and they rewrite it in a kind of AND or tree structure. And this AND or tree structure that captures, in a sense, the set of all proof trees. And that proof tree is what you see on the right. So they do certain manipulations on the logic to get this structure, and then the logic is turned into a proof tree, and the proof and this AND or tree closely mirrors that proof tree, but that AND or tree is then used as the basis for the neural network. And so what you see on the left part of the slide is the original AND or tree, but there have been some things that have been added. You see now that more connections have been added. You see also that there is this extra node, this gray node that has been added. And so they would manipulate the neural network a little bit, and then they would add connections and weights to it, and they would train it as any other neural network. And that's essentially what was done in those days. They then also had like mechanisms, because of course after training you get this weighted network, and they were also having techniques to get the logic back from the neural networks, or at least to get some kind of explainability reflecting the logic for that. And that approach is also still very popular today. You'll see key representatives of that also later on in the talk. And one of them is the approach by the Prague group around Andrei Kuzelka, where he's also building up in a kind of KBMC approach, using the logic, using a kind of proving kind of structure. You get a proof tree, and then you start adding certain things to that, like the activation functions and some aggregation stuff, in order to train neural networks like that. Another very nice system that we will also come back later on is that of the neural tier improver. And in the NTP, what you do is you start from a kind of prologue, and you do the kind of backward reasoning, the kind of proving that I've shown on some of these examples, like the smoking example and the original example. And once you've built up this proof tree, again, you put that as the structure of your neural network. But there is one very fancy thing in the NTP, and that's called soft unification. In normal logic, if you have a predicate smokes, then you have to unify that with exactly another predicate that is smokes. but yeah, maybe there is elements that are close to smoking and words that would resemble smoking. I can't come up with one like that, but you know what I'm referring to. And then it would still allow this to match in a sense. And whereas logic matches in a hard way, what the NTP does is it matches in a kind of soft way. And the mechanisms for that will also be discussed later on in the talk. In both cases, and that's a bit the downside of these approaches, what you see is that the logic is used to construct a neural network, and then you transfer everything to the neural network, and the network takes over and you get training. And at the end of the day, you get something that is very, very hard to interpret. That's why Shavlik and Towel were also trying to reverse engineer some of these networks and try to construct explanations already in these days. But that's a very, very hard task. And on the other hand, yeah, what you also lose is the power to do pure logical reasoning here. That is lost in these approaches because everything is delegated to the neural network. The neural network takes over in a sense. And so, okay, this was the left part. We had the directed and the proof theoretic based, and so that corresponds to the neural programs. The other perspective is that of the logic as the regularizer, which is reminiscent of Markov logic and very much in the same spirit. And there's a very nice and elegant example from Xue et al. At ICML in about 2 years ago, where what you have is a normal neural network, and then you want to enforce certain constraints on that neural network. And the first example they give is one for multi-class classification. And say you have 3 classes, and so there's 3 output nodes. Well, if you train, you would not want to get you would not get, you don't want to get a situation like this where it says, okay, P1 is true with probability or with belief 80%, P2 with probability or belief 30%, and P3 with probability or belief 90%. Because if you do multi-class classification, you want to get exactly 1 classification and not 2 or 2.5 in a sense. And so what they did, they had the insight that you can also use constraints and try to enforce the neural network to satisfy these constraints. And so one constraint that is very natural to have here is that you just say, well, there must be exactly 1 possible output. Exactly 1 of these output neurons should fire and none of the others should fire. Of course, this is a pretty extreme, a pretty logical, a 1-0 kind of thing. It either satisfies it, the Boolean logic, or it doesn't. And that's, of course, not very practical if you're working with neural networks. And so instead of this pure logical view, they turn that into the probability that the constraint is satisfied. And that's, again, very much in the spirit of this starry-eye logics, so to say. And here you see how you could compute the probability that this kind of constraint is satisfied. And it gives you a kind of semantic loss, as they call it. It gives you like a kind of degree that the constraint is satisfied. And this is then used as a kind of regularizer. So the loss would consist of the traditional loss function that you would have, like cross entropy or whatever. And then there would be the semantic loss that would be used as a kind of penalty. And they use the log of the probability that it is satisfied here. And that's, again, another very nice approach that comes back in many forms in the current neurosymbolic systems. In the work by Serafini and Garcet, This is coming back. Also there, the logical statements are are used as a kind of regularizers and will influence the structure of the network and will be used as regularizers. So again, the logic acts as a kind of soft constraint. Also in semantic-based regularization, it is coming back as soft constraints. And what you will see is that many of these approaches, they don't use pure probabilistic logics, but they use fuzzy logics. And that's also something that will be coming back later during this presentation. But what you see here as well is that despite the fact that the logic is used as constraint and you punish the neural network if it doesn't satisfy these soft constraints, again, the power to reason pure logically, like to do, for instance, proofs or to find models of a theory, that is kind of lost, the ability to reason at the purely symbolic level. And that's a bit the downside of a lot of the state of the art in neurosymbolic, that everything is left to the neural network, and then the logic is, so to say, forgotten almost. Okay, so that's concluding this first two dimensions. And I'm now gonna head over to Sebastian, who's gonna talk about the types of logic, which is the third dimension. So I'm gonna stop sharing and let Sebastian take over. Yeah. Unless there's any questions at this stage already. Don't know whether there's questions in the chat, but yeah, so the circuits in, so there's a question about the sum product networks, which are, of course, a probabilistic representation, which are in a sense also, they bear some resemblances, I think, to like this K-band approach. And so there's certainly connections to be explored there. And yeah, things like sum product networks are also used in some of the neurosymbolic approaches, like the deep problog that will be talked about later. So there's connections, but it's probably pretty deep at some point. So now I'm gonna head to Sebastian, unless there's another question.
I will start sharing my screen in the meantime.
Good.
Okay. So I guess there is no more question, and I'm gonna take over. So yeah, as Luke already mentioned, so the third dimension that we're gonna look into is the type of logic, and here are kind of the key message to remember from this part of presentation, really to be aware that there are different types of logic that exist, and they all come with different functionalities. And this is indeed something that is maybe a bit or tends to be overlooked in the nastier neurosymbolic systems. Now, if we start purely from the logical perspective, as Luke already showed, we generally divide types of logic in two different groups, namely the propositional one and the first order logic, with main difference being that the propositional logic, of course, only works with propositions, whereas in the first order logic, we introduced variables, and then it becomes much more expressive. Now, what is here kind of interesting is that even within the first order logic, there are many different flavors of logic or first order logic, starting with logic programs, which are really the programming language. Like you can really see them as being equivalent to having any kind of a programming language as a representation paradigm for both knowledge and the models that you want to express. And a typical example here is really like a Prolog, where it is, you can really think of it as kind of having every functionality of a programming language, working with structured terms, being lists, dictionaries, or any kind of data structures, you want to use being able to work with recursions and so on. A bit less expressive paradigm is that datalog, which is kind of a syntactic subset of logic programs, which is always guaranteed to terminate. So if we compare it to the logic programs, which are really maybe the most expressive paradigm that we can look into, datalog is really kind of a query language for deductive databases, meaning that it doesn't have the structure terms like lists and data structures, but a big payoff that you gain if you drop these kind of structures is that it's always guaranteed to terminate, which is of course not the case with logic programs. You can have infinite loops and then you never terminate. Now another or third interesting flavor of logic are answer set programs, which are logic programs that can have multiple models, but they still always terminate, and they do come with different interesting features such as soft or hard constraints, or you can even work with preferences over different statements. So this is really, so for example, here is a simple example where it shows that you can, for example, the answers that programs have these features such as choice rules. They can easily enforce constraints on your models and so on. Now, why this is important to have in mind is that, well, of course, different types of logic can do different things. So if we start with the simplest, this propositional logic, of course, that can do only the propositional reasoning. And then the more expressive paradigm is, of course, datalog, which gives you this ability now to answer database queries. Then going a bit more expressive, they can work with the answer set programs, which of course they can just do everything that datalog can do. They can do everything that propositional logic can do. And because of these soft and hard constraints and preferences, they are very interesting paradigm for modeling common sense reasoning and similar things. And then of course, something that is then on the top of the hierarchy, so to say, we have logic programs that can do everything that, well, at least almost everything that all the other types of logic can do, with the exception of answer set programs, and some of the features of answer set programs are a bit more difficult to model in logic programming, but logic programs are the most expressive paradigm. Now there is one thing that is, we believe, interesting to mention, is that we typically would put logic programs and first order logic on the same level and consider them interchangeable, but this is not really the case. And the simple example that we can look into here is this: if what we will call a transitive closure. In a sense, if you would try to model kind of paths or in a graph based on the edges, here you can say, for example, that there is a path between two nodes if there is an edge between them, or there is a path between nodes A and B if there is an edge between A and C being some kind of other intermediate node, and then there is a path between C and B. Now, what is interesting here is that if you work with logic programs, you get exactly the thing that you want to have. For example, if now we have only just edge between nodes 1 and 2, then you would only have the path between nodes 1 and 2. But this is not necessarily not the case with first order logic. And the difference is that logic programs always have one single model of their program or theory, whereas first order logic can have multiple models, so many models for the same theory. So they're not directly interchangeable, and these kind of things are worth having in mind. And maybe this is the biggest difference between logic programs and first order logic, is that we lose this transitive closure with first order logic models. Now, if we go back to NESSY and look at the project that exists in the NESSY literature, what this kind of the perspective of logic, what it actually tells us, of course, is which kind of problems you can solve with different NESSY systems. So one of the examples is semantic loss that Luke just discussed a few minutes ago, which is perhaps the simplest thing. It only works with propositional logic. Then we have that majority of NESSY systems are based on datalog, which is again a bit more expressive paradigm. But if many of the systems that you've seen so far, such as differentiable ILP, neural theorem provers, lifted relation neural networks, they are all built on datalog. Then there are very few things such as NeurAsp, that are built upon answers to the program, so they can solve even a bit more problems compared to the systems that are based on data log and on the propositional logic. And then there is a few systems that are then even a bit more expressive, such as DeepProblog or NLProlog, which are based directly on logic programs. And then to put them kind of in a same or almost the same bucket, there is of course a lot of systems that are based directly on first order logic, and these are the kind of approaches that are that operate with this notion of using logic as a constraint to a logical theory. So this is one interesting thing to really have in mind, is that depending on which kind of logic you use, that also changes which kind of tasks you can do. So this is going to wrap up the third dimension, and here really just as a key takeaway or a key message, just remember there are different types of logic and they give you different functionalities. And with that, then I will close this third dimension, and I will give it give the microphone, so to say, to Robin to continue.
Okay, thank you. So now we're going to talk about symbolic versus subsymbolic. So of course, neurosymbolic systems are going to have to look at both. So two key messages here that we're going to discuss is that, well, of course, entities are represented very differently in symbolic and subsymbolic systems, but just like what Niels is trying to do is that they're complementary, and then of course they can work quite well together. And then also that neurosymbolic systems differ quite a bit in exactly how they combine symbolic and subsymbolic properties. So to start off, let's look at the logic part first. So entities in symbolic AI are of course symbols, and that includes atoms like N and Bob, numbers and variables. But more interestingly is we have these structured terms, right? So we can represent relations with that, mother and Bob, or lists of varying length, or even more complex structures like trees and such like that. So these are very flexible, actually, ways to represent things. Now, what's also interesting to note is that, okay, these symbols are just identifiers for entities in our logic. They really don't have any inherent meaning by themselves. So if we have these facts about a family, for example, in the bottom left, if we just rename everything, then it still has the exact same structure, but even to us, it loses its meaning. So the symbols themselves don't really have a meaning by themselves. However, what we do have with symbols is we have unification. So this is a very powerful mechanism that's for symbol matching that's actually used in many AI systems and is used in stuff like automated reasoning. So it's really quite a powerful mechanism. And to put it simply, what it really does is it tries to find a substitution theta so that you make some symbols match. So if you have mother X Bob and mother N Y, then we can find a substitution, namely replace the variable X by N and Y by Bob. And then we know that these two are actually equal. So not only can we determine if the two of these terms are equal, we can also determine how to make them equal. So that's actually quite a powerful property. Now, it's less useful to look at similarity. So if we have mother and Bob, just exactly how similar is that to mother and Charlie? Now, intuitively, it's quite similar because we're like describing a relationship between twice a relationship of like a mother, but we can't really tell anything that are they similar or not. We can just tell that they're actually not unifiable. And then actually in some cases you could, if you don't take this into account, it makes it maybe more generalizable because it's a very hard decision that's being made at that point. So if we look at the neural side, so subsymbolic systems, well, you require different representation, and just for these, I'm going to call these non-symbolic entities subsymbols that they are represented by. And they are generally not quite as flexible. So where we had these structured terms which are very flexible, we see a lot in neural systems that they require a generally fixed sized numerical representation. And if we want to have something that works with something that's not fixed in size, then we have to account for that explicitly in the design of neural systems. So think about like recurrent architectures that can work with different like a number of vectors as input, but then again, the vectors themselves cannot, for example, change in size that easily. So then entities, so we have to have this translation from an entity to a subsymbolic representation. So often this is not even necessary, like images are obviously subsymbolic in nature by themselves, or the transformation is quite straightforward. Like if we're having a natural language sentence that we can, I mean, it's very standard to tokenize it and then turn those tokens into embeddings such as one-hot encodings or something that's learned embedding. Now, in some cases that are being looked at them more and more, like if we want to work with graphs in neural networks, then this transformation is definitely not straightforward. So we're trying to form something that's very well, general in its representational ability, like graphs, and try to fix it so that it's able to work in a more fixed representation. That's not very straightforward. So we can work with transforming it into a adjacency matrix, and then some additional matrices with node properties. But also here, it's not very straightforward how to do it, and I think there's still a lot of work that's going on to see exactly how this translation should happen. So these subsymbols, it's not that we cannot represent them in like starry eye systems, of course, in these symbolic systems, just because we have these very flexible structured terms, right? So we can easily represent vectors as lists and matrices as lists of lists. Now, an important distinction here is that they don't really become part of any of the computation mechanisms. They are almost just represented as constants in the logic, and they're not really first-class citizens. So if we can learn something, we generally won't be able to learn like the values inside of these. So it can be represented, but they are not really used to their full potential. Now, subsymbols, of course, if you consider symbols to have no inherent meaning, you could consider subsymbols to be all meaning, basically, right? They're what they're made of. The numbers they represent the entity completely, so they're basically just all meaning. And similarity kind of then, because of the numerical nature, be easily determined, right? So there's this metrics, like we can take an L1 or an L2 distance or a radial basis function. So there's a lot of choices there that you can do to determine similarity. But then it becomes equally hard to ask, like, when are two entities not the same? When are they very different? Or when are they equal? So that's really like the inverse issue that you have with unification. Now, this, of course, because of the way this works, usually leads to very generalizable systems. So if you have subsymbols that are close and very similar to other symbols, and we can also expect a fairly identical response from like a system to that entity. Now we can also extend this idea of similarity to encoding relations, right? So instead of just looking at the distance between two maybe vectors, that we can actually look at triplets, so a relation, subject and object, and then score that triplet by itself. And then we actually have a lot of ways to structure this embedding space. So if we look at how these are then used together in neurosymbolic systems, there are several ways. So one way is that you have symbols as subsymbols. So what do I mean by that? Well, it means that symbols are replaced by subsymbols. So this could be, again, a one-hot encoding or some learned embeddings, or you might even find some inherent numerical properties from a secondary information source. And this is very natural in systems that are actually originate from like a neural basis, that are they come from a system where you took your neural network and you added logic on top of that. So that's very similar to what we, for example, saw if we translate this natural language sentence. We basically assign every token in the sentence to a subsymbolic representation. So one system where this becomes very clear, that's been talked about previously, is the logic tensor network, right? Because there they introduce this idea of a grounding. And there they really specify, okay, for basically everything in our logical language, we have an equivalent representation in the subsymbolic. So constants are going to be mapped onto a vector. Functions are going to be mapped onto functions in a vector space, and predicates are also mapped onto functions that have that map onto the 0-1 range. And then on top of that, so the reasoning is then happens in soft logic as well. So if you look at a diagram, sorry. So if we look at the diagram, so this is a representation of a logic tensor network for a single logical formula. You see all the way at the bottom here, this is a step where we encode our symbols into this subsymbolic representation. And everything that happens on top of that is then the computation that happens in this subsymbolic representation or in this soft logic representation. So of course, if you also have the complete opposite, where subsymbols are replaced by symbols. So this means that this subsymbolic nature is not really considered in logic. So we treat tensors and vectors as symbols, and the subsymbolic properties are not really directly used in logic. However, the difference with a star AI system would be that we still make use of those subsymbolic properties somewhere in the system, and that's generally, of course, on the neural side. And then also, these are generally considered to be differentiable or learnable, so that they can actually be optimized as well. And this is more natural in systems that originate from a logical base. For example, DeepRoblog. So DeepRoblog is an interface between probabilistic logic programming and neural networks. And this interface takes the form of a neural predicate. So this means that we actually going to model the output of a neural network as probabilistic facts. So there is this interface that communicates between the logic and the neural side. So if we take as an example the addition that we've discussed before, we could actually implement that in two rules in DeepRoblog. So the first one is one of those neural predicates. So this basically means that we have an input, so D for digit, MNIST digit, and it's going to map that on an output that's from 0 to 9, and the probabilities of these are determined by the neural network, basically. And then beneath that, we have one single line of a logic that defines this addition. Namely, we're going to use this neural predicate twice to make the classification, and then we're going to do the addition in logic. So I've highlighted here in red the variables that would then actually be unified with the images, so the subsymbols in our case. So as you can see here, we would then have addition, 3 or 5 and 8. So here, the images are just represented as constants. There's nothing in the logic that's going to look at these images on the pixel level. This all happens in the neural side. So we just give that to the neural, and then the neural side is going to work with the subsymbolic properties and give us our predictions back. However, this might seem as a limitation, but it really isn't, and more about it later. But if we then look at just exactly how this is integrated, yeah, it's not okay. Okay, there we go. So if we have the same example as on the previous slide, if we look at what happens after inference, then we actually construct all the way at the end the structure you see on the right-hand side. So at the bottom, we see that we have our neural networks that have received the inputs from the images. And of course, they have made a prediction at the end. And that prediction goes through this interface, this dotted line, and then enters basically this structure here. So this is an arithmetic circuit that encodes the probabilistic inference that has to happen to actually get our answer. Now, this is also differentiable. So you see that the subsymbolic representations have become part of one big differentiable structure with respect to the output as well. So we can actually optimize and learn them and use these as part of the system. So they're not completely disconnected and have become first-class citizens. And it's actually interesting to look at it. So this looks very similar to the diagram for the logic tensor network, except that it's basically the opposite way around, because here at the bottom, we don't have symbols, we have something subsymbolic that is actually turned into something symbolic through the neural network and then is then reasoned with later. And to make this a bit more clear, so what if we really want to show that we can still do some nice stuff with this, even though we're treating them with them symbolically? Imagine that we want to encode a successor relationship between images. So yeah, imagine that this 5 is a 4, then maybe it makes more sense. So we would actually use a convolutional neural network to embed these two images, and we would encode those embeddings with the symbols E1 and E2. Similarly, we could have a learned embedding for the successor relationship, and we give that the name R. And then if we actually add R and E1, we get another symbol E3, and then we can actually look at the similarity. So this RBF predicate here looks at the similarity of its arguments. Now, this implements an idea that's practically identical to the TransE. So where the relationship is represented by a translation. Now, the important part is that all of these colored symbols here actually represent tensors on the computational graph on the neural side. So these are all connected, and we actually can build this computational graph and this TransE system in a declarative way using the subsymbolic properties only as symbols on a logical level. So this is not actually a limitation at all. It's just actually a nice way to work with them if you consider systems like these. And now another interesting case is where we have subsymbols as labels. So if you look at the field of star AI, then we use probabilities as labels, right? So we have certain atoms and they are assigned a probability of being true. And then inference happens basically by combining these labels. And for probabilities, that's just like additions and multiplications. And that happens, for example, in that arithmetic circuit as we saw like 2 slides ago. Now, if we look at subsymbols as labels, then of course, the labels themselves are just not probabilities. They become, for example, tensors. So this is what is done in the T-prism system. So here, atoms are assigned tensors, basically. So here we have a relation between a subject, a relation, and an object. And that's basically the conjunction of these 3 tensor atoms. And these tensor atoms basically represent, well, this is an atom that's going to be labeled with, and in this case, the tensor S indexed by Y. This is tensor O indexed by I, and tensor R indexed by I. So what does it actually mean? If we then look at the label of this relation, that actually is then defined as the label of this conjunction of those individual labels. And here in T-prism, that's actually implemented as a summation over the product of the elements at the same index. So this small program is then implementing this node, which is also this way of embedding relations. So, for example, so before we had trend Z, that's encoded in the declarative way. Here we're having Desmald encoded in a declarative way. Now we're going to look at the neural theorem prover. So it was discussed before. Now this is actually a very interesting system that is kind of a hybrid of what I've mentioned before. So the neural theorem prover uses both this symbols and subsymbols kind of simultaneously. So the symbols really retain their symbolic nature, but each symbol is also has this learnable subsymbol. We're going to call it T. So we can still, of course, do compare symbols using normal unification. And if we want to then compare subsymbols, they're going to use this similarity function, which is this radial basis function, which is defined like here. And then that's combined in what's called soft unification, like discussed before. And basically the idea is that you unify what can be unified. And if you have two symbols that cannot be unified because they're different, we can still look at the similarity of them in the subsymbolic representation and use that as kind of a score of how good or how much sense does this unification make. So, for example, let's say that we want to soft unify mother Ann Bob with parent X Bob. That would then look at, okay, now we're going to look at the similarity of mother and parent. So that would then look at the subsymbolic representations of mother and parent and see like how close are these in their subsymbolic representations. And then for the other arguments, we can just unify them normally. So we have to unify N with X. So that's just assigning the variable X to N. And Bob unifies with Bob, of course, so that we don't actually have to look at any similarities there. So you see that at this point, similarity and unification is happening at the same time, which of course allows you to do very nice things. Now, this is then of course used in the proving strategy. And that actually, so they construct this differentiable structure out of those modules. So they have an OR module where you try to apply every rule that whose head soft unifies with the goal you're trying to prove at that point. Now, this might, of course, be quite a few because soft unification is well, allows for far more unifications than normal unification. And for everything that unifies, we're going to then use an AND module to prove all of the sub-goals as in the rules body. And this AND module is going to try to prove this conjunction. And it uses an OR module again to prove the first goal, and then recursively is going to use an AND module to prove the remaining sub-goals. Now, if we're going to look at an example, so imagine we have a very small program. So we know that Ann is the mother of Bob, and we have this rule here. So that involves basically, so we're inverting the arguments here, right? So that's all we know about this rule. So R1 and R2 don't really happen in the rest of the program, but it's still some background knowledge, right? They have this inversing relationship. Now, imagine that we're trying to prove the relation that Bob is the child of N. Well, with this end-to-end differentiable proving, you can go two ways by proving this. You could try to soft unify this first fact that we know, mother of N Bob with child of Bob N. But then we have to look at how similar are mother and child and how similar are N and Bob. Now, if your subsymbols are learned and are somewhat what you would expect, you could see that this would get quite a low score, basically. Also doesn't really make sense that you would try to prove directly, that is, that Bob is a child of N out of the fact that mother is N of Bob by assuming that mother is the same as a child and N and Bob are the same person, which doesn't make a lot of sense. Now, the other way to prove it is to use this rule, right? So R1 XY if R2 YX. So that means if you soft unify this, that you're going to soft unify R1 of X and Y with child Bob N. So that means that R1 has to be similar to child, and then we can actually unify variable X with Bob and Y with the variable N. So then we have to prove the body of this rule, of course. And to do that, okay, well, we actually not going to use the same rule twice. So we have this other fact left over. Now, so we have to try to prove R2 N and Bob out of mother N and Bob. And the only thing that we then have to do, because N and Bob, the two arguments, unify, we have to look at the similarity of R2 and mother. So here you can already see, and that's something that's going to be discussed more in the future, that if R1 is similar to child, because their subsymbolic representations lie close to each other, and R2 is similar to mother, this becomes very equivalent to having that rule in your database, basically. So this is going to form the basis for rule learning in a differentiable way. But again, there's going to be more about this later. So let me get back to the key messages here. So these entities, if we present them with something symbolic or subsymbolic, you have very different properties, right? So very easy to find equality versus similarity on the other hand. If you have purely symbols only because they don't have any inherent meaning, it might be hard to generalize over symbols, whereas that's very natural in subsymbols. So this is exactly this kind of complementary approach that neural symbolic systems try to utilize. And then you can also see that they actually differ quite a bit in exactly how they integrate these symbolic and subsymbolic properties. So this is the part on symbolic versus subsymbolic. So I don't know if there's any more questions about this for now. If not, I don't know if we go into the break a bit earlier or...
Yeah, I think it is good now.
Okay, so...
Let's take 20 minutes. Yeah, let's take a 20-minute break. So we're gonna go back at 20, well, at 40. I don't know what time it is in your zone.
Yes, at 40, yeah.
Yeah, so in 17 minutes, in a sense. Yeah, that's it, right? Then we would restart.
Okay, so hi everyone, let's continue with the tutorial. So let me share the screen. Okay, so I hope you can see it now.
Yeah.
Okay, perfect. So then we'll continue with the fifth dimension. And this dimension actually considers learning. And now kind of the key messages or what we want to show in this dimension is really to understand what learning is in this kind of systems and different flavors of learning that do exist. And in that case, we'll start with Star AI first. And we are talking about learning. Well, we are thinking of the very similar process as we do things in machine learning, is that we start from data, which is in this case, if we are working with this kind of logical data representation, that can be any kind of data, be it the knowledge graphs represented here, sequences, even traditional tabular representations. So we want to go from any data, consider knowledge graph, to our probabilistic and logical model, answering certain questions over that knowledge graph. So if you look at the types of learning in Star AI, they are typically, well, we consider kind of to have two different groups of learning approaches or learning paradigms. which are different with respect to what they are provided with and what is the learning goal. So the first group or first paradigm is structured learning, in which we start directly from data. So the only thing that we are given at the beginning is just data, and we have to figure out the model and its corresponding probabilities, which is essentially the learning goal. So we'll say here that we want to, in structure learning, we want to learn both the structure, meaning the logical formulas, and their corresponding parameters. Now on a different side, or the different paradigm, it's parameter learning. And in this case, we start from data and some kind of discrete structure. So right, we have both data and logical formulas. And what we want to learn are the parameters of the logical formulas or the probabilities. So to just make sure that we are really here on the same page. So when we're talking about parameter learning, so we have the data, we have some kind of logical formulas that are given to the model by the domain expert. And really the goal of learning is to just learn the corresponding probabilities of the logical formulas. When it comes to learning principles, you can think of the parameter learning as learning any kind of parametric model. Think of like the things like logistic regression, neural networks, and so on. The same parameter learning principles apply to this case. So there are learning approaches based on gradient descent, least squares, or expectation maximization approaches. So this is kind of very similar to what most of the machine learning does nowadays. And then if we move to structural learning, then of course, then we start from having all of the data or having all of the knowledge graphs, and then we want to learn both the formulas and their corresponding probabilities or weights, depending on which kind of model we use. So if you would be using probabilistic logic programs, then these things here would be probabilities. If we are using things such as Markov logic networks, then these would be just the weights. Okay, so this structure can be further divided into two other groups, namely the discriminative, where we do have some kind of target concept or target relation we want to learn. So for example, if we look at here, for example, you can see that every rule here has the kind of the nationality in the head of the rule, and this would be the target concept or the target relation, and to learn how to basically decide what's the nationality of people and so on. So in the discriminative learning, we have the target relation, and we want to basically learn a model that, learn logical formulas that describe this relation from the background knowledge that's provided. So you can see that is the rest of the knowledge graph. Now on a different note, we have the generative learning when there is no specific target relation. And what we want to learn is kind of a generative process behind the data. So how kind of learning the process that would generate exactly the same type of data. Learning in Star AI typically, especially if you talk about structural learning, follows this idea of learning by searching, right? If we start from some candidate formulas, you can see, for example, that we start from very simple formulas. We learn their corresponding parameters, we evaluate how good our model is, and then if we are not satisfied, we create new candidates or refine the logical formulas. That's what I mean when I say candidates. So we can refine that further to get more complex formulas, learn the parameters again, evaluate, and then repeat this loop until we find a satisfactory model. Now, you can immediately see a problem in this kind of, and the main challenge in these structural learning approaches in Star AI is indeed to control this combinatorial enumeration. So we just enumerate formulas, which means it can very quickly become a very difficult problem, and you really need to control the complexity of this space of formulas that we are going to explore. Now, just to give you a bit more sense, what does learning by searching means? So just we look at the one particular approach called deep Propfoil Plus, and you look at this Simpsons example. So imagine that as our data, we have the family trees among Simpsons, And what we want to learn is expressed only in terms of things like spouses and the children and the children and the parental relationships. And what we want to learn is how to basically learn a model that captures the idea of, or the concept of, grandparents. So we have some examples of grandparents. So what Propofoil does is that, of course, it starts with an empty model, just having absolutely no formulas. And the way how Propofoil Plus controls the complexity is that it learns rule by rule. So it learns a single rule. Once it finds a good rule, it adds it to the model and searches for another rule. So as a simple illustration, what Propofoil Plus will do, it starts from a very simple rules that simply say have our target relation in the head of the rules, and then the body is just set to true. And this, of course, means that basically that every pair of people would consider it a grandparent relationship, which is, of course, not the rough definition of the concept. So we would refine further with the hope to find better models, better logical formulas. And refining simply means that we're going to add the predicates that we have available to the body of the less complex clause. So if we started from everything being a grandparent, now we say here, for example, that we'll define a grandparent concept in terms of mother and father predicates and so on. And if this is, again, not good enough, right? So we can further refine all this, the logical formulas that we found to get a more complex definition of the grandparent concept. And then in this case, we find a satisfactory rule somewhere here. At that point, we learn its probability and just add it to the model. And at this point, we would just start again by finding a single rule to enhance, to add to our model. So this is how Propofoil controls this complexity, by learning rule by rule to add to the target model. Now, a different approach to controlling this complexity is that we can leverage random walks, and this is something that's very popular in Markov logic networks. And that we can start from our knowledge graph and then simply traverse it. And then in that way, what we can identify are kind of paths in our knowledge graph that are kind of frequently occur in our data. So here, for example, you can see that there is a path or a random walk that starts at the book, then moves to one of the 4 students, which you can further connect to some of the professors, which then can be connected to other group of students and then to another book. And then having identified these useful paths, what these type of methods do, that they can turn every path into a clause or a rule in the model. So that's simply, if you can see a path in the model as kind of forming a conjunction that can be turned into logical formula. So this is another way how to control the complexity or the combinatorial complexity of learning. Now, if you look at both of these learning paradigms together, well, so that if you look at the structural learning, of course, the good thing is that we can start directly from data. We don't have to think about anything else. But as a disadvantage, we get really complex combinatorial problem, and which typically means that the user would needs to design or define a language to use for constructing the model, so that the problem remains tractable. Now, if you look at the parameter learning, of course, learning is much easier and it scales much better, but we need to provide the rules, and the models are typically quite sensitive to the choices of these rules, because if you provide useless rules, then of course you cannot get a good model, and you really need to provide useful rules if you want to get a well-performing model. Okay, so that was the StarAI perspective of learning, and now we're going to move to the NACI, or the neurosymbolic learning perspective. And so what we have is StarAI is really this, so to say, dichotomy, right? We see we differentiate between structured learning that starts only from data and the parameter learning that starts from data and the structure and form and logical formulas. Now, what is interesting in the NESSIA approach is they now add this entire spectrum of different ideas how to tackle learning. And now I'm gonna guide you through each of these individually. So one, or kind of if we look at what is really the problem with star AI learning techniques is that they search for these rules or logical rules or clauses systematically. So what you get is really this kind of an exhaustive search tree where you start from very simple a logical formula, then you move to more complex ones, and then you really systematically traverse the space of possible rules and that you can define. Now, one very interesting idea coming from NESSIA is that we can, of course, introduce preferences or try to learn preferences over different primitives, different predicates that we can use to construct our models. And then we don't have to traverse the search space exhaustively anymore. We can really traverse it selectively and focus on most informative parts. And how do we know which primitives are useful for individual problem? Well, we can learn that from data. And this is exactly what DeepCoder does, which is introduced by Balog in 2017. So kind of the idea is that what behind DeepCoder is that it changes the learning problem in the sense that we are not learning, what we learn from are the pairs of, well, examples and a program or a model that solves these examples. And then having the model available, we know which kind of predicates or which kind of programming primitives we need to solve a certain problem. And which means that we can also learn how to predict a function or a probabilistic model that tells us, basically defines a distribution over the primitives in our language, or how likely individual functions or predicates are, kind of defines the likelihood of using individual functions to solve a task given by a certain example. So what we can do once we have this conditional distribution that we learn from our data, and given a certain example, right, we can just use the examples to estimate the probability of functions belonging to the target model, the target program, and then we can use these preferences to learn more efficiently. Meaning, what DeepCoder does is it first look at what are for example, the most likely functions or predicates to be used, and these, for example, these three here, these three here, and these three here. Now, what it does is start to construct the program using only these primitives. And then if it's unable to find a program, if it's unable to find such a program, what it does is that it then extends with less likely function until it is able to find a program. Now, following this idea, of course, there is the DreamCoder that is now introduced by Ellis in 2018. It generalizes this idea of DeepCoder towards the modeling the distribution of entire programs rather than just individual primitives, and it uses neural networks to model this distribution. So kind of the neural networks take examples as an input, and then they are able to give a probability distribution over individual programs, not just the primitives anymore. Now, another idea that still just uses the data and nothing more than that are the neural Markov logic networks. And if you remember from the beginning of the tutorial, when Luke introduced Markov logic networks, one interesting interpretation of Markov logic networks is that they can be actually interpreted as Markov networks, just in terms of probabilistic graphical models, which can be then written as this kind of log linear models, right? That we can have the probability of a certain world is as we can define as kind of product of different potentials or factors, and what these potentials, or where do these potentials come from, and they actually come from the Markov network that we obtain by grounding out the Markov logic networks. Now, what neural Markov logic networks do is that they replace essentially where these potentials come from. They're not anymore coming from the grounded model, which is the expensive part, but actually come directly from data. So if you look at here, for example, let's say we have our very simple knowledge graph here. What we can do, what they do is what Markov logic networks do, or neural Markov logic networks do, they partition your data in different fragments and then define these potentials directly over the fragments of data rather than fragments of the grounded model, which is a much more tractable problem to solve. Yet another approach that's really, or this is one really interesting idea that still uses only the data, is that we can circumvent this combinatorial explosion or combinatorial search by actually using, instead of exhaustively exploring the space of models, we can actually use a neural model to generate discrete structures that we then test symbolically. So for example, with this approach introduced by Maxwell Nye and Brendan Lake in 2020, that it starts from the examples, encodes the examples into some kind of embedded space, some kind of neural representation or latent representation. And having this latent representation of the examples, we can sample discrete models from it. In this case, these are simple grammars. And then having these discrete models, we can actually test them symbolically whether they solve our test problems. Okay, so these are all of the approaches that still use only the data to start with. An approach that is really middle ground between both structure and parameter learning is something called program sketching, in which the idea is that we provide a partial code and then leave some of the functionality. We leave what we call a hole. There is a missing functionality which is to be filled with, for example, neural networks. So for example, if you look at here are a few examples that basically square each element in the list. If you want to learn such a program or a logical model to solve this problem, we can specify part of a problem and then simply say, here is the missing functionality. And I really want my neural network or any kind of other model, we want that model to fill in the missing functionality. So we really here provide some of the structure, but not all of it. And that's why it's between the two extremes. Now, so here's the title is wrong. This is the structured learning via parameter learning. And this is likely the most prominent learning approach in the NESI part. Is essentially the idea is that we can use parameter learning to learn the structure by essentially enumerating lots of logical formulas from certain templates, and then we can learn just the probabilities or weight of these formulas. Now the idea is here, if we compare to the parameter learning in Staria, is that of course in Staria we're typically very selective with the rules that we provide for parameter learning. And here we're just gonna enumerate really lots of them. And then just, if we have a hope that our model catches that if there is a certain rule that is useless, then just assigns it probability of 0 or something very low. So if you look at our Simpsons example again, so the kind of the difference here is that we would start with program templates. And this is kind of, you can see it as a kind of a higher order rules, meaning that in our logical rules, we also don't only have variables over the constants, but we also have variables over predicates here, right? So we can fill in and instantiate the predicate variables as well, not only the constants anymore. So if we look at, again, we have our target predicate or target relation that we want to do being a grandparent, and we have some other background predicates, which are father and mother. So what we can do, we will start from the template and really just instantiate, So in the head, we put our target predicate. So this is the grandparent only. And then in the body here, for example, this P is the predicate variable. We replace that with every, background predicate that we want to use. In this case, it's only mother and father. Then we move to another template, we do exactly the same thing, and so on. And now enumerating these rules from the tables really gives us really like a lot of rules. And then we can do just a parameter learning over these set of rules. And this is kind of the general idea. And this is the most prominent, most often used approach to structured learning in NESSIE. Now, if you look at all of these NESSIE learning approaches, they all have, of course, different pros and cons, different advantages and disadvantages. If you look at the neural guidance, as in DeepCoder and DreamCoder, well, their advantage of these kind of approaches is that they make the discrete search tractable by focusing on important parts. But of course, disadvantage is that we typically need lots of training data to be able to do that. If we then look in the soft patterns, such as the neural Markov logic networks, what we get is really efficient learning over some kind of relational data. But then as a consequence, we never get this explicit structure. So it means that we cannot really interpret what's being learned. Then if you move to neural generation, where we use the neural model to generate discrete structures to test. Of course, we can again make this combinatorial search much more focused on training on the interesting parts of the search space, but of course that's not that easy to train. Then if you look at sketching, we do reduce the combinatorial complexity by providing part of a structure, but that still requires the significant user effort to define the initial structure. And then if we move to the structured learning via parameter learnings, then we completely remove the combinatorial search. But of course, we can get some spurious interactions, meaning that even probability or the rules or logical rules that have low probabilities or low weights can still make an influence if there is a large amount of them. And then this is something that's very difficult to anticipate and to even understand and debug. Now, so this finishes the learning dimension. And here really the point is that when it comes to learning, we have these two types of approaches. One being structured learning, when we learn both logical formulas and the probabilities, and the parameter learning, when we are only interested in learning probabilities of a predefined model. And of course, that the NESSIE approaches to learning now add a bit more nuance to it, and they open many new directions to learning. Okay, so this finishes this fifth dimension. And with that, I will give a word to Giuseppe, unless there are some questions that I can answer immediately.
I will share my screen in the meanwhile. Okay. Can you see my screen?
Yes.
Okay. So if there are no more questions, I start. Okay, this sixth dimension is semantics. So we have already talked about semantics in many different points during the presentation, but we will now go more vertical about it. So the messages that, let's say the key messages for this dimension is that in the end, StarAI and NESSIE share the same semantics. So we'll talk mostly about StarAI semantics because in StarAI, they are just the same. And moreover, we will see that the concept of seeing the semantics as a function implemented by a parametric circuit is very useful because when these circuits are differentiable, then this view, let's provide the easiest way to make a neurosymbolic integration. And finally, we will see also that there is this concept of reparameterization so that you can see some of the NESSIE models just as reparameterization of StarAI models. So let's start with, okay, what is semantics? All of you know that when you describe some formal language, you give two pieces of information. You say, okay, this is the syntax, so this the set of symbols and the rules of how to compute them. But these symbols, so the syntax is just symbols. They don't mean anything, like these 42 and 47 here. But in order to give meaning, you need to assign a value to these symbols. So when we talk about semantics, we talk about providing values or denotations to the symbols. For example, if we say, okay, 42 is the property of being a human being, and 47 is the property, or is the Greek philosopher Socrates, then okay, now you start to understand what you are meaning, and you can say, oh, human Socrates is true. So semantics is in general about providing a value to element of the language. So if we consider for simplicity just propositional language, so where we have prepositions, operators, and we compose sentences using preposition operators, then a very useful concept is the one of labeling function. So since we want to give value to elements of the logic, let's talk about a function that is this labeling functions that takes an element of the language and provides a value. So we go now to compare different semantics for logic, probabilistic logic, and neurosymbolic system. Let's start with pure logic, and of course we start with Boolean logic. In Boolean logic, the labeling function is a function that assigns to element of the language just one of out of two values, or true or false. So it's a two-valued logic. And okay, and how can we define an entire labeling function for any sentence? Well, we start first of all by providing labels for the single propositions. So if we have three propositions A, B, and C, then we provide labels for each of them. And this is, let's say, I put a tilde on top of the L here because they are kind of parameters. We are basing all the semantics on these basic labels on the preposition. Then, of course, we have to provide the semantics for the operators, and these are the well-known truth tables. So you give a truth value to all the possible combinations of the arguments of the operator. And finally, the semantic of any formula, so any sentence of the language, is just defined recursively on the labels of its components, of the operators and of the proposition. And this recursive definition is very interesting because it is said to be an extensional approach, in the sense that you can look at this like a computational way of defining a semantics. You start by the sentence that you want to label, you parse the sentence, so you explicit the recursive structure, and then giving a label to the sentence is just like a bottom-up evaluation of these three. So there is kind of, and let's say the tree that is on the right here is like a circuit that takes the values of the propositions and compose them to provide you on the root the value for the entire sentence. And this is a very interesting view because it will come later in all the semantics that we are going to look at. Now, the second pure logic semantic is the fuzzy logic. Now, fuzzy logic is when you have not just two values, but you can have many values. And now we are going to look into a particular subclass of fuzzy logic, which is called T-norm fuzzy logic. Now, in T-norm fuzzy logic, things are not just true or false, but they can take any value between true and false in the real set. So we consider the real interval 0, 1, and the labeling function is just a function that assigns to each of these element of the language a value between 0 and 1. And again, the process is just the same as Boolean. First of all, we provide labels for the prepositions. So we say, okay, look, this preposition A is valued 0, 9, is true 0, 9. B is true 0, 3, and again these are the parameters of the semantics. And then we need to provide labels for the operators, but now arguments are a real value between 0 and 1, so we need not tables, not truth tables, but functions, truth functions, and we use the T-norm theory to do this. So T-norm is a binary function that, so it takes two values between 0 and 1, and it provides one value between 0 and 1, which has the meaning of the conjunction. So the T-norm is the extension in the fuzzy case for the conjunction. So there are three fundamental T-norms. You see it there. There are the Lukasiewicz T-norm, which is the sum truncated to 1. Then you have the Gödel T-norm, which is the minimum between two elements. And finally, you have the product T-norm, which is the product within the two. And you see that all of this behaves like conjunction in the sense that if one of the two is low, then the entire conjunction is low. So this is the way of extending, let's say, the Boolean operators in the fuzzy case. And you see that if you have exactly 0 or exactly 1, then they behave exactly like Boolean logic. And all the other operators can be derived from the T-norm and another linked operator, which is called the residuum. So in this way, you can define all the functions that maps to the operators. And finally, if you want to label again a general sentence that defined in this logic, you apply a recursive approach. So you start from looking at the root operator and you go down in the tree. So again, fuzzy logic is extensional. So the same workflow that we have seen before, it's very interesting. But there is a good, very nice addition here that fuzzy logic and T-norms are continuous and differentiable. So the circuit now that you see on the right is a differentiable circuit. So you can differentiate, for example, the root with respect to the leaves, which is very useful as we will see in NESI. So this is the link to the NESI systems. And however, fuzzy logic is not Boolean logic, of course. So they have different properties, but there is one, let's say, a common standard in neurosymbolic to use fuzzy logic as a relaxation for Boolean logic. And this relaxation can introduce, if not used very carefully, undesired effect. For example, I put here an example. Suppose that you want to impose in a Boolean way that A or B or C is true. And this means, of course, that one of the three should be true. But if you map this, for example, into Lukasiewicz T-logic, then you are imposing that the minimum between 1 and the sum of all the fuzzy values of the proposition is 1. And suppose you optimize this with some magic optimizer and you obtain the solution that you see at point 3 here, so that A and B and C are all equal to 35, then the constraint, the fuzzy constraint is satisfied, okay, because you sum 35 3 times, and so you have something that more than 1. But if you defuzzify it, so you return into Boolean logic, so usually you just put a threshold to 0.5, then you see that all the 3 are false. So you see here that something that is very normal in fuzzy logic, like aggregating truth degree, is not good in Boolean logic. So usually using fuzzy logic as a relaxation for Boolean logic can be a problem if not done properly. So let's move now to the, let's say, probabilistic logic. So let's add a level of semantics on top of the pure logic semantic and what is done in probabilistic logic. Here again, we're talking about a labeling function. We still want to apply some value to the elements of the language, and this value is a probability. But now the way of defining this labeling function and this semantics is very different with respect to the other ones. Again, the first thing, we should provide some basic parameters for the semantics, and this is can be done in different ways in probabilistic logic. For example, you can provide labels to proposition. That is what is done, for example, in Problog. So you say that, for example, the proposition A has probability 0, 1, but you can also provide labels for formulas of interest, and this is what is done in Markov logic, where you say, for example, that the weight of the formula A and B, it's 1.5. And this label here, it's an atomic label, is not the final label, the probability that we will get. Here, indeed, in Markov logic, they are just, let's say, unnormalized probabilities. The second step is, okay, now we use these labels to introduce a probability distribution over assignments. You have already seen it in the look part, where you say, okay, we have our possible word, and we want to know, okay, what is the probability of this possible word? So suppose that the assignments in the possible word are A equal 2 and B equals 4 for two proposition A and B. What you want to know, okay, what is the probability of this joint assignment? And this can be done in different ways. For example, the first one is the one of Problog, where you say, okay, given all the given a possible word, its probability is the product of all the true proposition in this word times 1 minus the label the label of all the propositions that are false in this possible world. And let's look as an example. This is the example that Luke showed you before. So where you have a burglary, earthquake, earth alarm, and then an alarm rule. Now here, the probabilistic facts are just the three: burglary, earthquake, and earth alarm, John. And so you want to describe a probability distribution of assignments. So these are all the possible assignments to B, E, and H. And let's look at the one before the last. And suppose, okay, what is the probability of this true, false assignment? You just take the true, the label for the true assignments like it is, and 1 minus the label for the false assignment. And you make the probability, and you get, for example, this 0, 0, 2. And you can do this, of course, for all the other words. And in Markov logic, instead, this is different. In Markov logic, an assignment is proportional to how many groundings this word satisfy of a given formula. So suppose you have a given formula like stress X implies MOX X with a weight like 1.5. Then you ground this formula, so you substitute X with all the possible substitution, and you obtain this tree grounding, let's say stress N, smokes N, and similar for Bob and for Carl. And in this word, in particular word, just the first one and the last one are true, while the second one is false. So the probability of this word here, again, is proportional to the weight of the logic of the formula times the number of groundings. So in this case, 2, 1 plus 1. And then in this way, you can construct all the same table that we have seen before. And finally, okay, we want to know a way to label any possible sentence in the language, like we did for the other semantics. And the way of doing this in probabilistic logic is using weighted model counting. So the idea is that you go over all the possible words, and you see which of these words satisfy the formula, and you sum the probability. So you are counting the possible words that satisfy the formula, and each of them contributes with a weight that is its probability according to the probabilistic distribution. So if we look at the same Problog program, and you have the sentence that you want to label B and H, what you do, you go over all the possible words, and you just pick the ones that are where B and H is true, like these two, true, false, true, and true, true, true. And you sum their probabilities, and you get the label for the Q. The problem with this semantics, as you see, is that the probability of a sentence like A and B implies C is not just a recursive functions of the labels of the parameters, because you, of course, should take into account the large dependencies that are in the probabilistic structure of your problem. This is the disjoint sum problem that Luke showed you before. However, one of the ways of attacking this problem is by using knowledge compilation. In knowledge compilation, what you do is very simple as idea. You start with your formula, and you translate your formula into another formula that is logically identical, but that now explicit the probabilistic structure of the program. And if you do this, then you can, in order to get your count and then your label for your formula, you just evaluate the formula. So the extensional approach, even though not directly applicable like in the other semantic, is still very valid. So also for the probabilistic semantics, we have a parametric circuit that we can encode to describe the semantics of a formula. Now, before moving to the neurosymbolic, I want to show you another possible probabilistic logic, which is probabilistic soft logic. And the idea of probabilistic soft logic is okay, even though Problog and Markov logic network are reasoning about Boolean assignments to value. We want to know if A is true or B is false. Here you want to reason about fuzzy assignments. So it's again, let's say, the superposition of a probabilistic semantics on top of a logical semantics. But this time the logical semantics is fuzzy. And the shape of the distribution is just the same. What changes is just that the grounding are just not true or false, 1 or 0 like before, but can take also, let's say, intermediate value. But the nice thing of this is that now the probability distribution is a continuous function. For example, if you consider this form, the probabilistic soft logic that comes from the formula stress X implies MOX X, the same from Markov logic, the first thing that you do in probabilistic soft logic is that you translate it into a fuzzy formula. And now this fuzzy formula is differentiable with respect to the parameters, with respect, for example, of stress X or SMOC X. So one interesting problem here is that, okay, can I maximize the value, the satisfaction value of the formula with respect to the labels of the single proposition? Then you can do this, of course. You build the circuit. This circuit is differentiable, so you can differentiate with respect to the root, which is the label of the formula, and you try to maximize the root with respect to the parameters. And you can do this, of course, with back propagation. And then once you have the gradient, you can use your gradient in any gradient maze optimization algorithm. So you see that some links already are in there that will bring to neurosymbolic, which is the next step. So how can we carry these exact semantics, these exact circuits to the neurosymbolic case? So this is the question now. And the key here is that this labeling function can be just mapped to parametric circuits. And there are some of these semantics that are differentiable. Now, what are these circuits? These circuits are, let's say, computational graphs where the structure is determined by the query, the sentence that you want to evaluate. And the leaves instead are scalar parameters that you have provided in your first step. Remember, the first step is providing this L tilde for each semantics. So so what you are doing here at the beginning, for example, when defining this problem here, you're saying, okay, for burglary, I give the probability 0.1. So you are setting its in a table, it's scalar parameter. Then for earthquake, its scalar parameter is 0.05. So this is a table. And so then you can, when building the distribution, you ask for burglary and you get its corresponding value 0.1. So why can we translate this table into neural network? And this is the trick that many neural network systems do. So they take the same approach. I want to give atomic labels. So these parameters to proposition, for example. Why don't using a neural network to do this? And the reason for doing this, okay, there are many reasons, but two of the main reasons are, of course, a neural network can index much larger spaces. So you can use, for example, for burglary, you could use an image, for example, of a security camera, or for earthquake, you can use the sensor. This, you, of course, cannot give a parameter for all the possible earthquakes or all the possible images, but a neural network can instead index this space. But also if you are in a completely symbolic space, then you can exploit sub-symbolic spaces like embeddings to have, let's say, a more efficient indexing. And this is what I call reparameterization. So the idea is that you start with the circuits that represent your semantics in the logic or in the probabilistic logic. And what you do, you turn these leaves that are the parameters, which are scalar parameters, with neural networks, with output of neural networks. So you keep the semantics completely the same, you just parameterize it into a different way. And it turns out that you can do this for many star AI systems. So if you start with PSL, what we have seen before, where you want to maximize, for example, the value of the formula with respect to the labels of the atoms, then there are two systems that are called semantics-based regularization or logic tensor networks that you have already seen that just do this, takes these scalar values and translate them into neural networks. So instead now of maximizing with respect to the scalar parameters, you maximize with respect to the parameters of the neural net. But the semantics, which is the structure, the shape of this circuit is just the same. It's the same of PSL. And of course, you can do this also by reparameterizing probability distributions, so the probabilistic models. For example, in Problog, you have seen that what you do is just multiply these labels on the propositions for the true and the false facts, while in Markov logic, you weight the formulas. And for both of them, what you do in the end, you have to make this weighted model count and a way of doing this is just by compiling it into an arithmetic circuit using knowledge compilation. And so when you have this, let's say, circuit, which represent a Problog or a Markov logic distribution, then you can reparameterize it and you say, okay, I don't want just scalar parameters, but I want neural networks. And this is what is done by deep Problog for Problog and by relational neural machines for Markov logic. So you have the same exact circuit, identical. So the semantics is completely kept identical. You reparameterize it with neural networks. And I just show you an example of how this is done. For example, in deep Problog, there is this idea of interface. So you pick one concept from the neural network, in particular, an output of a neural network, and one concept for the probabilistic logic, in particular, a probabilistic facts. And you say, okay, I collapse this to a same concept, which is a neural predicate. And so if you have, for example, for Problog, you would have had some burglary with probability 001. In a neural predicate, you have digit, for example, which is labeled by a neural network that takes a representation, for example, of an MNIST digit and provides its probability. So the semantically, they are the same. It's just how you parameterize the probabilistic facts with scalars or with neural nets. So to conclude the message for this dimension, we have, let's say, seeing that the semantics in Starry Eye, in most of the cases, are just the same. You use the same semantics which are Boolean, you use a fuzzy, and you use probability, especially these last two, because they are differentiable. And a nice way of looking at this semantic is the fact that you can compile the labeling function into a circuit. And this circuit, let's say, remembers the networks that you have in deep learning, the differentiability of the networks. So you can use the same kind of ideas there. And finally, you can see some models, some neurosymbolic models, just a simple reparameterization, direct reparameterization of Starry Eye models. Okay, and with this, we end the sixth dimension, and we move to the last one, which is, let's say, easy one, a very, let's say, a general dimension that looks at the three main paradigms that we have looked today for the neurosymbolic, which are logic, probability, and neural networks. We have these three paradigms. And the goal for neurosymbolic is, of course, we want to integrate these three paradigms. And we argue that if you really want to integrate different paradigms, you should recover the base paradigms as special cases, because otherwise you are sacrificing something. It's not a real integration. It turns out that in order to keep all the properties of the base paradigms, you pay a price in terms of complexity. We'll see it. So in general, what most of neurosymbolics do, they sacrifice a bit of the base paradigms in order to be more scalable. But of course, they don't, let's say, recover all the properties of the main paradigms. So in order to show this behavior, we will use this kind of radar chart. Here we will position systems to this spectrum, and the closer a system is to a corner, then the most it recovers that paradigm. So let's start, of course, with Starry Eye. And Starry Eye, by using the distribution semantics, perfectly integrates the probabilistic and logic view. So you can do whatever you would do with probabilistic graphical models, and you can reason exactly in the same way you would reason with logical system. And of course, you can compose it into more expressive systems. So you recover exactly these two paradigms, but Starry Eye was not interested in the integration with neural networks. Another class that is instead neurosymbolic here is the one that wants to integrate logic and neural networks, no? And we have relaxed theorem provers. You have seen a couple of these examples like K-BAN, LRNN, and neural theorem provers. All these systems just pick a theorem prover like you do in Prolog, so with backward chaining, and you add some weights or some soft operation in order to be able to make some kind of soft reasoning. But usually when you do this, you don't preserve anything. And you don't preserve, everything from the main paradigm. You are sacrificing something, and you cannot reason purely logical anymore. So this is the price that you pay when you had this weighted reasoning. Another class of methods like semantics-based visualization, semantic laws are used as regularizers. So the idea is that you start with a neural model. So you are keeping everything from neural networks, and then you use logic and probabilities as kind of regularizers. The problem is that this logic and this probability is used only during training, and you push everything into the weights of the network. But then when you want to predict, so at inference time, you just drop the logic, drop the probability, and just use the neural network. So again, you are not assured to behave purely logical or purely probabilistically. Another class of methods that was mentioned during the symbolic versus some symbolic dimension is knowledge graph embeddings. So the idea of knowledge graph embedding is pushing relationships and knowledge graph into an embedded space. So they are not really logical. Sometimes they do some kind of probabilistic description, but they are, for example, mean fields on all the atoms, so everything is supposed independent. So they are not very probabilistic or logic. And also from the neural side, they don't really recover all from the neural networks. They just recover embedded space. However, thanks to this, let's say, sacrificing a bit from all the paradigms, they are very scalable. They are usually the most scalable solutions in the neurosymbolic scenario. We have also graph neural network. The graph neural networks, let's say, built on top of the knowledge graph embedding from a neurosymbolic viewpoint, but they also had this capability of propagating informations from multiple layers of the embeddings. So they kind of mimic the multi-hop reasoning that is common in logic, like in proofs. And so they are from a, let's say, are a bit better from the logical viewpoint. However, there is not really logic in there. So if we want to say, are they recovering logic totally, then we cannot say they are. And the last dimension is the probabilistic reparameterization that we have seen in the sixth dimension, that are the system that just pick star AI models as base, and then they extend by reparameterizing them with neural networks. And let's say that they, of course, use the same semantics of a star AI system, so they recover probability and logic perfectly. What they are not still very good at is using the entire capability of neural networks in the relational domains. For example, they cannot use subsymbols at the level of the reasoning like graph neural networks do, but because they want to keep, let's say, the logical reasoning as main paradigm. So let's say they don't recover neural networks very well, but they have the possibility to use sub-symbolic spaces like we have seen, for example, in DeepRoblog or relational neural machines. So again, just to conclude, we have this spectrum that is made by logic, probability, and neural networks. And we would like for the integration to be able to, for an integrated system, to recover all the cases. However, this is usually very complex to do. So the common solution is to sacrifice a bit of the properties of the base paradigms in order to obtain more scalable system. And with this, I have concluded this part. So I leave the word to Luc to conclude. Luc, you want to share your slides?
No, maybe it's best that you go to the next slide.
Okay. Okay. So.
Okay. Yeah. So I guess the point of this tutorial was really to try to point out a lot of similarities between star AI and neurosymbolic. And in a sense, what we have attempted to do is like dissect to kind of decompose star AI and its components, and then see whether these components come back in neurosymbolic. And we've done that along these 7 dimensions, like the directed versus undirected, the proof versus model-based, the kind of different ways of learning structures and parameters, the different ways of assigning semantics, fuzzy, probabilistic, or logical. And yeah, these symbols versus the sub-symbols. So all of these dimensions are in a sense coming back and provide evidence for the kind of commonalities that exist between these two areas. Still, I must say the area is still in, it's still very early days. And so there's still a lot of open questions. I mean, there's more open questions than I think things that are fully understood today. And it's a very interesting and very fastly developing area. I think after this conference, we'll have to adapt again the tutorial to add a couple of new papers and systems that are being developed. But there's very interesting questions to ask, like which properties should integrated representation satisfy? We kind of tend to believe that, well, as Giuseppe has argued, that if you combine different frameworks, that you want to have at least some of the power of the original constituents, and ideally you want to have it all. But of course, that comes also at a kind of price to pay. And one question is also, if you have a particular application in mind, can you then design a representation that has the right kind of combination to do the job well and perform well and be elegant? Another thing is, like, we've also illustrated, I mean, Giuseppe was talking about pipelines versus interfaces. At some point, he was showing really the interface and this neural predicates between a neural network and the logic. The other thing that you often see is that there is a pipeline that, okay, you first have a step that takes, for instance, the logic and maps it into a neural network, and then everything is done there almost. And you get like this one directional flow. The nice thing about an interface is that it goes in both ways, right? That it goes from the logic to the neural networks and it goes back. And that's ultimately, I think, what we would like to see and what we would like to have. And we want to make the interface, of course, as large as possible so that in the logic you can work with the embeddings, and in the neural network you can, yeah, do some kind of logical issues. That would be like some of the ideals that we have. And I guess the last question I already answered or tackled. And then, of course, yeah, once you have the representations, the question is, which learning techniques, which inference techniques are still applying? And there, do you need mixtures of the things, or can you resort to the originals, so to say? So that's then at the level of like using and developing these tools. That's a pretty intricate question, and there is where all the technical work lies, in a sense, because one of the key problems is, of course, scaling up while retaining as much of the semantics that you want to get. Could you go to the previous again? Yeah. Yeah, like one of the things is also like there is these choices that you can make, like the gradient is very fashionable and very efficient, of course. That's also why people resort to not to pure logic, because in pure logic everything is discrete. So you need to go to the yeah, to quantify certain things and work with parameters. And then there's the choices, probability versus fuzzy. A lot of people choose for computational reasons the fuzzy, but it seems to be that there is also like this semantical price to pay. That at least some things that you would expect hold in pure logic no longer come back in fuzzy logic. And probably there's other things you can do in fuzzy logic that you can't do it in the pure logic, but still it's not entirely equivalent. You also want things to be explainable. And the hope is that, of course, neurosymbolic, if you already combine the perception with the knowledge and the logic, that you get something that's inherently more explainable. I mean, logical reasoning is much more explainable than, well, weights in a neural network And so maybe also by combining this, the neurosymbolic is kind of interesting. And then the question is also like how to evaluate it. I mean, so far there's a lot of different systems, a lot of different approaches, and every system comes with its own experiments and data sets. And once in a while, okay, a given data set is used by the next system. But I think we're still far away from, you know, being able to apply this on a large scale on impressive applications. It's still early days. And ultimately, you would also want that you get this 1 + 1 = 3, which means that you can do everything that the neural network does, but also everything that the logic does. And you would be able to do something more, something extra that neither the logic nor the neural network alone can in a sense do. So that's like the 1 + 1 = 3. So maybe we should go to the next slide. And yeah, so there's a lot of different challenges. I think this is a perfect area for starting researchers, for PhDs, because it is hot. It is like where everybody's going and where you can expect results by the time a PhD is finished. That this will become more fashionable and will even be useful at that time. That will work on applications. And so there's a lot of challenges, like which applications is this good for? Which model should we be using? And how to control the complexity of inference and learning in a sense. So with this, I think that's probably the last slide that we have. There's still, so we'd like to thank you for being here. And of course, we're very open for questions. We did reserve quite some time for questions. So I would say, feel free to fire the questions at any of us or put them in the chat. And I see there's already one for Giuseppe on where would TensorLog and differentiable ILP lie in the pyramids.
Okay, let me think 1 second. Okay, I would say that they are kind of like differentiable provers, because in the end is that what you get from both the systems. So yeah, I would say that is in the sense that they don't really cover probability, and they are neither neural networks nor logic, but in between. Let's say they try to merge choose things, but you again cannot reason purely logical because you have weights in there. So it's not discrete anymore. And yes, also from the neural network side, well, I think that maybe, for example, TensorLog and NLProlog, that is one extension, they can do something more that other neural theorem provers. So yeah, they are more pushed to the neural side a bit more than others. Yeah, I think.
Just wondering whether there's other questions. Another question from Prasad for Giuseppe.
Yeah, this. Okay, the other way around. So, I think, yeah, of course, is non-trivial. I don't know if it is impossible. I don't know how to answer right now. It seems, yes, that you should lose something, but yeah, okay. Of course, someone asked about some product networks. Is of course, if you start using structure in a very, let's say, templated way, where you just add neurons that behaves like rules, but behaves more like hidden neurons in a neural network, then you have some way of taking, like, say, a neural network and see it as a parameterized circuit. But yeah, it's, let's say, a bit hard to say that it's really logical in a certain sense. So I don't know. Let's say that yeah, it's an open question. It's something that one should look at also.
Yeah, thank you.
Any further questions or?
Yeah, I have one more question. This may be a speculative thing. Is there a killer app for this combining star AI or neurosymbolic approaches? Is there an application where nobody else can outperform this combination?
Well, one thing that comes to mind and that we're hoping, but it's not yet a killer app, it's like some things you can do quite elegantly is like you can compute. Like if you work with the Prologs, you can really compute things. And you have a programming language. And so, for instance, this multi-addition seems to be something that is pretty hard for some of the other systems. I'm not saying it's impossible. I haven't checked them all, but I think that would be something that I expect to be hard for other ones. But maybe, yeah, Giuseppe or Sebastian.
I would say that, of course, there is now the trend to think that neurosymbolic can solve everything because it's a function, let's say, universal approximator, and of course it's true. But okay, one thing is for a neural network to learn a discrete process, and one thing is to tell the discrete process in a very elegant way, very general way that easily generalized. So I think that in general, this is the case. Yeah, neural network can learn, but for example, when you start having less data, then heavy kind of knowledge that you can push, and the more clean this kind of knowledge is, like the logic knowledge is, the better you can do. And this seems to be the case in those few applications that try to make this. But to answer your initial question, there is not a killer application. And I think this is something that is really slowing the advancement in this field because it's hard to find a real strong application, at least now. So it's something that all of us is looking for. I don't know if the other agree with me, but.
Yeah, I mean, I would agree, well, both with Giuseppe and Luke. I think this strong advantage is this ability to compute and you can just accumulate stuff like working with lists or any kind of data structures. But yeah, I think all think there has to be some kind of killer app, but we have problems thinking of it or something that could be handled with the current technology.
I have a question about a killer application. Why, you can get DeepProbLog and add a neural network to it and just add a little bit of logic on top. And, it sounds like it would do better than just that neural network alone because you're adding a little bit of knowledge and you're not placing a lot of overhead. So suppose you go to Google or to Facebook and they're using a neural network there for some reason. I say, well, you can use DeepProbLog with this very same neural network that you're using, but you can incorporate a little bit of knowledge and it's not going to cost much more. Wouldn't that be a killer application?
It would, yes, I think it would. It's just that we haven't done it yet, so.
All right, so.
And yeah.
If I can add one thing. There's also an interesting case where we looked at the addition problem with DeepProbLog, but we also included label noise. So there was a certain fraction of the labels were just completely randomized. And if we take, for example, DeepProbLog, and we not only just define this addition, but also we added the idea of noise. We encoded that in the logic as well with a learnable parameter that basically tried to estimate how much noise was in the data. And then we actually show that also with this addition of the logic, but not only that, but it's very specifically here the probabilistic logic, because you have to think probabilistically about how likely is this example noise. We show that with this small extension, we're not able to make, for example, a model that's more robust, but also one that's able to figure out how much label noise there is in the data, basically. So even if you were to have the case where you have 100% noisy data, we see that, okay, we don't really get a good accuracy on a test set without noise. However, we do see that the model notices basically that's all noise. So I think that's one of those areas might also be a very nice application for the logic with the neural and probability on top as well, which is, I think, really also what the Star AI brings to the picture.
Any other comment or?
There is a question I see. I'm reading.
Okay.
I think maybe I can add to that. I think these kind of languages like Web People and Pyro, they are a bit difficult to analyze in this in our over our 7 dimensions because they don't have an explicit logic component to them. But they can do right there. They can do reasoning in terms of having a probabilistic reasoning. Of course, because they are full-fledged programming languages, they have a connection to logic, but it's not as strong with, for example, these the things like, for example, Problog and Markov logic networks. And in this respect, they're a bit difficult to position over our 7 dimension in the sense that they would be missing some of those, and it would be difficult to put them concretely somewhere in the other dimensions that we could complete for them. So it's kind of a non-answer, but I hope at least just because it is difficult to also position these languages, at least in our analysis so far.
Yeah, so in that regard, we're not claiming that we cover everything that is kind of neurosymbolic or goes in that direction of combining things.
Also because if you look now at the deep learning new models, they start to add, let's say, this kind of discrete or relational thing in a very, let's say, soft way. So let's say that a lot of also very recent models like GenANS, this is the question about GenANS that someone make. They are, let's say, difficult to position because, let's say, they are GenANS. What is GenANS? There are many GenANS and they have different degrees of using, for example, logical knowledge or knowledge graphs. So let's say that deep learning is moving toward adding symbolic stuff inside their approaches. So a lot also new of the things that are thought like deep learning are already a bit neurosymbolic. So it's very interesting to start to characterize this. We started with this, but I think that there are a lot of other systems that can find a place into this description we made that are not in here. So yes, just to add something to the same.
Yeah, and the key goal is really to do what you do well, I think there's 2 key goals. Like one is really to be able, if there is knowledge, that you're able to incorporate it, and using that with the tools of logic, which have proven to be interesting and have also been developed over so many decades, and so to not lose that power in a sense, but even to increase it by combining it. All right, it seems no further questions.
No.
Okay, then thanks for attending, and it's good to see some of you of the familiar faces again. So I guess we may meet in the next couple of days at AAAI again. So see you.
Thank you. See you around.
Yeah, see you.
You.